Thank you. And I'll let Kathy and Krista take it away from here.
All right, I'm going to share my screen if that's okay with you, Kathy.
Yes.
Okay, I figured as much, but if it wasn't, I figured you'd also holler. So let's see. I wonder which one I just chose. This one, I think. Okay, oops, that's not the one I thought it was. That'll be fine though. All right. And now my screen of all the faces disappeared, so I won't be able to see you apparently because I have too much stuff open. I'm Krista Wood, and my colleague is Kathy Koenig. And Kathy is probably going to limit her talking a little bit because of a throat issue, so we'll be kind of trading off. Actually, you know what? I think I need to get out of this screen and go to the other one. I'm going to stop sharing this because I won't be able to bounce between things if I. This is the one I meant to do. I've got a lot of things open to make sure I can show things as I need to. All right. So, slideshow mode. Back to where I meant to be. Now I can see you guys too.
That's good.
So Kathy is at University of Cincinnati at the main campus, and I'm at the two-year college that's part of the university. So it's considered a regional college. We're an open access two-year college, and that's why I'm part of the TYC community as well as being part of the University of Cincinnati. Kathy, do you want to say anything? Are you good?
Well, I had throat surgery, which is why I can't talk very well. So I'm not sure if I can be heard or not. Okay, shaking heads. So I will interject when I can.
All right.
Thanks, Krista.
So you guys are stuck with mostly me for this one. So the goal of the workshop is that we want you to leave with concrete ideas and strategies for integrating the activities and question prompts into your own curriculum to promote specific abilities in scientific reasoning. So this is the outline for what we're intending to accomplish in these 3 hours. Probably a little bit ambitious, but we'll see how it goes. We usually do a 4-hour in-person workshop at AAPT in the summer. So this is along those same lines, just a little expedited in places. So we're going to establish the rationale for the focus on scientific reasoning. We'll define the scientific reasoning skills, provide an overview of the lab curriculum. You'll work through an activity for the first 3 sets of labs, also expedited. And then we'll talk about the assessments and the research on the effectiveness. The resources will be in OneDrive, which I'll show you how to get to before we get into everything. And at the end, we're hoping to have some time for you to plan how you can incorporate in your own labs. So as you know, we're constantly bombarded by social media from Google, from blog posts, reviews, news, YouTube, and all other kind of places that you get your news. Some of the examples are social media use increases depression and loneliness, or coffee drinkers may live longer, or sweet dreams, eating chocolate prevents heart disease. That's my favorite, quite frankly. But these news headlines in the social media tend to make statements that are more causal in nature, but they don't necessarily have the evidence to back them up. And so we read these things, and our students read these things, and what should they be? What should we believe? Does it have any impact on what you do, or should it? And so that's what we're going to kind of dissect here, is the skills in order to know what to believe and what is actually has valid evidence to support that. Okay, so a sound decision-making framework. We need to know where and how to get complete data. We have to learn to discern and filter the input. There's just way too much of it. And synthesize that data that we do have. even though there's a large amount. And realize some of the data, some of the inputs that we have don't weigh as much as others. Some are a little bit more important to consider. And all data, all news has some type of bias, and we need to recognize that. And apply the context and the meaning to the data for your own purposes. So we also need to refine information through analysis, such as final decision is based on knowledge that has a high degree of accuracy. So these were some of the sound decision-making framework aspects that were cited, were in a Forbes leadership column.
So we have had funding for about a decade now to develop curriculum to help students develop skills so they can be sound decision makers. And the lab format is perfect. It's absolutely perfect for teaching these skills. And so this slide just shows some of the skills that we target in our curriculum that align with scientific reasoning, but also we'll be teaching these skills that we're interested in. And so this slide I'm not going to really talk about, but I pointed out because this is the theory that underlines all of our work. And
have them an interest, right? They self-selected to be in this program. And as the days,
I'm not sure where that's coming from.
Hey, Chris, could you mute people that are not intentionally making noise? If they're intentionally talking, don't mute them. So.
I have been muting. I was a little slow on that one. Apologies.
So most of our work is based on the work of Deanna Kuhn and her theory evidence coordination framework. But I list the other ones because you might have heard about those. And we have a paper that came out about a year ago that explains the theory that we're using in our work, using the above ideas and also our reasoning tool.
So our assessment tool that we call iStar.
Yes. So here's the framework that underlies all of the labs that we do. And so theory evidence coordination means, so our students come into the classroom with existing ideas, and we have to pull those out and get them to understand what their ideas are. And then in the lab class, they're going to run experiments to really test their ideas, which is the evidence part. And then at the very end of an investigation, they will coordinate their ideas and their evidence with scientific theory. And so one of the things we've learned is students cannot go through this process one time. They need to go through it again and again, and it has to be very deliberate. So all of the labs, and we're going to take you through one today, all of them use this cycle or this framework. And we use question prompts and activities to get students to go through these thinking processes. Without them, without the questions, they don't go through it. And the skills that we really focus on are in the bottom corner: control of variables, data analytics, and causal reasoning. And those are the definitions. I won't bother to read them to you, but when we use these words, that's what we mean.
And these slides are in the OneDrive that I shared with you this morning. And so we'll show you where to find them as well.
Mm-hmm.
So AAPT has recommendations for physics labs, and we just have the slide here to indicate that we are well aware of those. We incorporate those into the lab curriculum. And so if you haven't seen this, I think it was 2014 that this came out. But we do follow, we have all of these aspects in the lab curriculum that we're showing to you today. So some of the features of our iStar curricular framework is that we have a guiding set of operationally defined scientific reasoning skills, the three of which were mentioned in the previous slide, and deliberate skill-based practice in both hypothetical and inquiry-based lab settings. So the hypothetical might be either in the pre-lab activities or also during lab, to get students to think about these different ways of different examples beyond just what we're doing in lab. And there are formative and summative assessments during each SR for each SR sub-skill as well. And so the instructor provides the scaffolding using a Socratic dialogue where we're having checkpoints, or in some cases I use whiteboard meetings to have groups review things and check their understanding. But the key here is that we don't just do it once. We build on those skills by having different context and giving them the opportunity to practice. So an example of a set of labs that work on building these skills are the first 3 labs of the semester of the curriculum. And all 3 use the context of a pendulum, but the key, and we have the same research question, what impacts the period of a pendulum? But the key for week 1 is, how do you design a controlled experiment? And so these are the skills that we're trying to get them to be able to do, identifying the various variables, dependent, independent, control, write a testable hypothesis, create an experimental design, and start to learn graphical analysis and how to make a claim and support it with evidence, because that's a skill that they don't have coming into our labs. Week 2, we then work on how do you measure uncertainties and then display those as error bars. And then we talk about systematic and random errors. So basically, identifying, quantifying, and representing uncertainties is the goal of week 2. Week 3, we get into creating the mathematical model and reducing the error. And also, they have to write a lab report. So for each of these, they write a group lab record by their group, but then at the end, each individual writes a group lab report. So each lab, we have a before, a during, and after. And the activities include some type of pre-lab where it's an introduction to skills, deliberate practice, and hypothetical scenarios. For the first 3 labs, Kathy has introduced IVETs to replace our original Word document with then a quiz to go with it. And that's been received really well. Unfortunately, they take a lot of time. And so that's still work in progress for the rest of the labs. So during the lab, they have the practice and checkpoints or whiteboard meetings, depending on where these labs are being done, and group lab records. And then after lab, they have a reflection and synthesis, which includes the lab report after the 3rd lab. And at the end of the lab course, there's also a final exam. And, so the interactive video enhanced tutorials are actually up on Compadre as well. And they started out for problem solving, but they're now slowly being integrated into the lab for pre-labs. So some of the other context that we have in the lab curriculum for the rest of the semester includes research questions. What impacts the acceleration of a system? What affects the period of an oscillating spring mass system? What factors impact the moment of inertia of a rotating system? And at the end, to have an opportunity for the students to apply their scientific reasoning skills that they've been developing, we have a design challenge. And that is, what factors impact the speed of a windmill blade system? And they have a lot of fun with that. So for the first one, we're going to have an example lab activity. And so we're going to have you engage with portions of the pendulum lab, alternating between instructor and student mode. So at times we'll be talking to you as if you're the instructor, and other times we'll kind of model how you would interact with students. So at this point, I'll need to I see some questions in the chat. Does anybody, should I be addressing those? I'm not very good at doing both at the same time.
Nope, we're fine. I'll call out if there's a question in the chat.
All right, thank you. All right, so the Lab 1 materials include pre-lab content, pre-lab quiz, and in-class instructions. And the students actually use digital copies of the instructions so then they can cut and paste into their lab records. So in the pre-lab for the introduction to experimental design, we always identify learning objectives both for the pre-labs and the in-class activities, the lab activities. And for this one, it's identify independent, dependent, and control variables, distinguish between a research question and a hypothesis, and write a testable hypothesis, which means that the hypothesis is very deliberate in being tied into the experimental design. So what's included in a pre-lab written document? Well, we define these various variables. We introduce them to an experimental design template. So we use different graphic organizers throughout the lab curriculum. And the first one that they encounter is this experimental design template. And then they practice examples. And in the pre-lab, there's answers provided. And then they either take a quiz or for the first 3, they actually work through an IVET activity. So as you can see at the bottom of the slide, if you're interested in incorporating any of this, you can go to Compadre. You can also contact Kathy for IVETs, lab IVETs to use at your institution. You can incorporate it into your learning management system. We use Canvas, so Kathy's got some SCORM files for that. All right, so for this one, this is our first lab, and we have a mass on a pendulum, and we have the students, we provide them with the question, what impacts the period of a pendulum? And in their groups, they have to jot down what are some factors that might impact the period of pendulum. So let's see. We have digital copies of this on OneDrive, but I think we can probably just brainstorm these factors. So think about that. And what factors can you think of that affect the period of a pendulum? You can just call out.
Should we just jump in with comments? Is that what?
Well, what factors do you think could affect?
Okay.
So we're trying to figure out what independent variable should we test.
Well, let's see. The mass of the pendulum.
Okay.
How far you pull it back from rest.
Okay. So when you say how far, how are you going to measure that?
The angle.
Okay, good. Anything else?
How long
Length.
sorry.
Go ahead.
I was going to say how long that string is.
All right. Anything else?
It could be the kind of string you have. In other words, whether you have a thick string or a thin string or something like a ribbon, chain.
So you're right. The students come up with a lot of different ideas, and some of them include the mass of the pendulum, the length of the string, the angle or pulled back from release. Sometimes I hear air resistance, and sometimes we hear acceleration due to gravity. They don't always come up with all of those, but then that's our role to guide them to, the factors that we actually need them to test. So what impact as we frame this, what impacts the period of a pendulum? The students come in, as Kathy had said, they come in with their own ideas. And so we just finished that first block. What are your own ideas? And when I say that, I'm saying as students, what are the ideas? And so we listed those. Usually I have those, them work that in groups, and so the ideas are often length, mass, angle, gravity, air resistance, and there can be other ones. And so then you have to kind of guide them to the ones that that we have time to do during lab, because we have time limits as well. So then they conduct the experiment to generate evidence to support or to refute. So if they said one of these or more than one, affects the period of a pendulum, what evidence do you have to support that? So that's this step. So the experimental design template, we give them a blank one that looks like this. So they put in the research question, and we do give them the research question for sets of labs. In this case, it's what affects the period of a pendulum. And so with that research question, we guide them into, and the pre-lab guides them into identifying the dependent variable, and then we pick an independent variable. So for every independent variable, that there's going to be control variables. And so they have to list that in this template and a hypothesis. So when they're finished, it should look something like that with actual values for length and angle if we're going to test, does the mass of a hanging object affect the period of a pendulum? So that's what it's going to look like, but they get the blank one to start. And on the bottom of the slide, you can see where some of these ideas were built from. So at this point, I'd like you to, I'm going to, let's see, close this out so that I can show you where this is. So the folder on the OneDrive, if I had your email this morning, then I shared the OneDrive folder with you. And so if you go to the link that I shared with you, hopefully you can find it. And you should have something that says 2023 AAPT workshop, UC Introductory Physics Lab Summer 2023. And that's because Kathy did a workshop in Sacramento, and instead of to make sure that everyone has the same, the curriculum stays as it gets updated, we just put the new stuff, which is the handouts for this workshop, in that folder. And that way you'll have all the curriculum. So how are you guys? Are you able to get to the OneDrive okay? All right, so you should have in 2023 AAPT workshop, and I need to move that down so I can get to it. And when you click on that, you should get all this stuff, which can be rather overwhelming. Thanks for indicating. And so what I need you to go to is this lab 1. So this lab 1 that says lab 1, intro to experimental design. So hopefully you found that. And when you get to that, you'll see a bunch of files, and we're going to go to intro to experimental design updated for fall semester 23. So that's the one we're going to go to. And it should look like this.
Quick question. For those who didn't get the link, should they try to get to it now or just watch from your screen?
Well, because we're going to go into breakout rooms, then if somebody in the breakout room needs to have the link, because I wasn't planning to have that open. Obviously things can always change, but basically I wanted you all to be able to get to it.
But if one person in the breakout room has it, then it should be
Then we
okay.
should be okay.
And Kathy just said if you send her an email, she'll try to send it to you as well.
Oh, I see there's lots in the chat. So Kathy's really good at, well, she's really good at all of this, but when she's not speaking as well, she can share things electronically quite efficiently. So if you've got access to the, moved it down too far. Okay. So in the breakout room, what we're going to have you do is actually work through lab 1. And so you'll see that we just figured out what the factors are that we could test, and with the instructor, you would narrow that down to the 3 that we're going to test for now, which are mass, length, and angle. But in the breakout rooms, you'll have 4 different roles that the students will take. And I want you guys to act like students, and there should be 4 people in the breakout room, hopefully. One student will be a data recorder, and that's the person who will open up a Word document. They'll start writing the lab records, and they can use a Google Docs, depending on the group of students. That tends to expedite some things so that all of them can work on it at the same time. They'll be responsible for downloading or sharing the Lab 1 instructions in OneDrive and cutting and pasting into the lab records. So that's what that student does. The second student is what we call a materials manager. For this workshop, we're going to be using video files. And so they will have the video file folder on the laptop for use during the lab, the data and manager or analysis. And then in-person labs, material managers would be handling the equipment and directing that as needed. The data manager or analyzer will open an Excel worksheet and a blank one and start filling that in. And then the directions tracker. So one of the things my students have trouble with is actually reading the directions. And so that person is responsible for making sure the group reads the directions as well. So these roles end up being really important for the success of the lab, this style of lab. So what questions do you have? Are we in a position that we could do breakout rooms? So we have 24 participants, and that probably includes all of us. So I think what I'll do, because I know some people are coming late and some people have to leave a little early, I will make breakout rooms for 5. So hopefully we have a reasonable amount.
Would you like me to do that, Krista?
Actually, it says 3 to 4. Kind of neat. Okay, we'll do 4 breakout rooms. I'm just randomly doing that, and they're open, but if you have questions, feel free to ask. And in the meantime, you can ask for help. All right, so let's see. We probably can pause the recording if you want. So I realize that you didn't really have enough time to work through it, but we're basically trying to introduce you to the materials, as much of the materials as we can during this 3-hour period. So thanks for your efforts. And I want to go ahead and, just recognize what we were hoping is that you would interact with at least one set of videos and figure out how to get some data. And then you're probably going to run into some of the questions that the students have as to how many videos should I use or how many data points do I need? And that gives us as instructors the opportunity to have students think about that. And why is it that the number of data points that you had really isn't compelling, doesn't lead itself to compelling evidence? So as Kathy had mentioned to one group who had 3 data points, that wouldn't be enough to pass a checkpoint. So I'm going to go ahead and share my screen and go back to the note.
Krista.
Yes.
I did a modeling workshop at Arizona State, and this is the first lab that the students work on. And when I did it in my class, what we went through the same kind of discussion at the beginning of how can we do this. And what I did was divide my group so that I have at least 2 groups of students that were checking one of the variables. So there would be like 2 groups doing mass, 2 groups doing length, 2 groups doing angle. And then I did the type of string, okay? And, and I purposely didn't have them go do everything, but they had to come back together to realize that very often in a science area, when you're studying things, you don't do all of the work, but you have a collaboration that has to come. And
So you're making a really good point,
that
Trina,
can
that we
validate.
do, science is about a collaboration, and that's
Yeah.
the emphasis is we use those roles in our lab to get that point across as well. So you're making really good points that we do introduce in this lab curriculum. And so one of the things is you worked as a community in your groups on hopefully at least one of the factors. And so if you had time to actually put it into Excel, you might have had a graph that looks something like this. And so we have, we emphasize, we put the independent variable on the horizontal axis and the dependent variable on the vertical axis. And so this is actually real student data that was used. And you can see that as mass changes, the period doesn't change. So what about the data that you guys came up with? Did you test
One other
mass?
point about the data that comes up on the variables that do not really alter the time for the cycle is that I found students really stretching their graph so they could have different places. And that brings up the idea of significant figures and the measurement tools that you have to use. And so they then volunteered to collapse their graph and recognize that there was no change.
And
Okay.
so
And
you're also actually leading us into our lab too. So we do look at uncertainties and how to reduce error, but we don't do that until lab 2. Our students we found that students really need to focus on one set of skills in lab 1. And so this set of skills is how do you design a controlled experiment? How do you collect data? How do you decide how many data points to collect? And so the checkpoint that the instructor has is to make sure that the students have a valid process and to guide them through that. Or if they don't have a valid process, to talk through where they need to make some adjustments. So this would be the experimental design template for mass. You'll notice that we have the research question. The dependent variable is going to be period for all 3 factors. And this is just an example of having the control variables and then the testable hypothesis. So here, we don't do a mathematical model yet. We just look at it and say, is there a relationship? And so we'll talk more about that. We'll do each factor at a time. Did anyone get some measurements on mass? And how many measurements did your group take?
In room 1, we got 3 data points for
three data points for group 1. Okay. And 5 data points for another group. Go ahead and speak up because
We got 3. We got 3.
Okay. And Chelsea, I saw you got 5, I think.
Yeah, room 3, we did 5 of each one.
Wow. Okay. That's great. Okay. So what we talk about is 3 data points. How many, if you had 2 data points and you wanted to determine what the relationship is, what do you always have if you try to fit a best fit curve to 2 data points? And then we go on to, okay, align. And then if you have 3, how confident are you in that data? And the more data you have, the more confidence you have in that model. And so that's the kind of conversation that we have. So is 5 enough?
And it's also the range of data. Students don't think about range.
Yes. And that's a very good point. So with using the videos, since we're limited, you're limited in a lab setting as well, but using the videos, we encourage them to take some from each end of those options and also in lab to have that range there. All right. So essentially from this data that I have on the screen, we can make we can draw the relationship as no correlation between mass and period. When, and this is a big when, we have the control variables, the length is an angle of release, and G are held constant. And so we have to emphasize that this is a valid relationship when these are held constant. And that's not something that students necessarily think of as we're doing this in Lab 1. So length, at least one group got some length. What did you see?
In our group, we only did stuff on the lower length side. We did like the first 5 data points, and then we deliberately put the linear line that our students would all put on it because it looks very linear.
And you're right, it does. And so that emphasizes the need for that range that Kathy was talking about, because when you look at a small segment, then your relationship is valid for that small segment. And we want them to have as reasonably large range as possible, given the constraints of lab. But also that correlation is found when mass, angle, and acceleration due to gravity and shape are held constant. So we have that opportunity to talk about this relationship is valid when, and only when, these other things are held constant. And then what about period versus angle of release? What'd you find with that? Anyone get to it?
We found that it seemed pretty much constant. Based on the limited data we took, I think we went up to 30 degrees or so.
And you're right, that does seem, it's hard to tell, with that narrow range of data. But as you go farther and get larger and larger, it's the pattern seems to be a little bit more that it isn't constant after a certain point. And so this outcome, the experimental outcome, states that with the data I've got here, that for angles less than 20 degrees, there was no correlation. And that's very clear to me. But as you go farther and farther into larger angles, then there does seem to be a positive correlation. And so there are times when you're going to have different ranges have different relationships. And so we can talk through that with the students as well.
Krista, when you're doing this one, do you ever take the opportunity to remind students about limits on equations?
Limits on what?
On equations or on a relationship. You're headed to equations, but in this case, there's no change for a period of time, or in this case, for a collection of the angles. But now, then we begin to see a change down here. And when I've done this with my students, I let them reach the point that there could be a limit on the validity of the equation.
Right, and that's what I'm trying to get at here. That
they do that in lab 3.
Have a hard time with that.
They do that in lab 3.
Right. So as Kathy said, we get into the mathematical model, the experimental model in Excel in lab 3. But in this first lab, we just limit that we say no correlation as long as we keep small angles. And we define that small angle as 20 degrees in this case.
And it's really what their data says. We don't care how good their data is as much as that they can interpret it at this point. So they might have something else to say here.
Can I ask a quick question? So at the checkpoint 1, if I understand it correctly, that's where the students are going to describe their planned procedure. So would you at that point make sure that they think about a broad range of angles, or do you talk to them about it? Talk to them about that, or? Okay.
Yes. As the instructor, I do that guidance.
Okay.
So as the instructor, that students need a wide range. You know that they need enough data points. Even after I tell them, they don't always collect enough data points. But
yeah,
so
because I'm thinking, they would be tempted to say, oh yeah, we go up to 30 degrees, that's enough, and we don't see anything going on, so we're good, right?
And so that gives us the opportunity.
Yep, you'll catch them later when they look at their models compared to other groups.
Okay.
So this first lab, we're trying to just get them to design the controlled experiment and start thinking about ways that they can improve. I see a hand. Go ahead.
So I noticed that we did the angle too in our group, and I noticed that the choice of angles 5, 10, 15, and then after 20 it goes by 10. Is that the student choice? Because this is, I mean, the choice is very nice, but is that aware, or is the students aware of the small angle?
They are not
Effect?
necessarily aware of the small angle. This data set was
Yeah.
created so that we could do online labs
I
during the
see.
pandemic. In lab, it's dependent on what the students choose with the guidance of the instructor.
Okay, okay.
You know,
Got it.
we do prod them toward make sure you test these small angles,
Okay,
but, and also a large range at this point.
thank you. Mhm.
Good question. All right. So basically, from this data, we're saying when did the end, you know, when did something change in this graph? And that's where we decide what part is no correlation and at what point is there a positive correlation. So this actually sets the stage for error bars and quantifying uncertainty, which we do in lab 2. But for this lab 1, we used what we call an outcomes organizer that Kathy created. And so we have all the independent variables that we test this week on the left side, length, mass of object, and angle of release, and the dependent variables on the right side. And this is a visual organizer that helps students put all those ideas together. At least that's the intent. And so the length, the experimental outcome is what we're addressing at this point. And in this case, our experimental outcome was a positive correlation when mass, angle, acceleration due to gravity, and shape were held constant. So we have the correlation for the experimental outcome and what were the controls? What were the limits to the claim that we're making? And we did that for all 3 of these independent variables. So what do you think about this experimental outcomes organizer? Does that look like something that would help students be able to organize their claims? So this is new in this academic year, and we're actually going to build a little bit more into the experimental outcome organizer as we go along. But for this first lab, I think that just keeping it to the correlations and the conditions for which this relationship holds is important. I tried to do a little bit more in the fall, and I like the idea of just keeping it to the relationship.
So can I ask a quick question on that? So what do the students do at this point? Would it come empty without the words positive correlation, and then they have to fill that in on themselves as,
Right.
or, sorry?
So
So
we give them a template that has 3 ovals and the
Okay.
one big shape,
Oh, I see.
and then they fill in the in-between
Okay.
based on their outcomes.
Okay, thank you.
So, just following up on that one, okay, so do the students come up at this point with this positive correlation, no correlation? Do they have an idea of saying that, or just doesn't affect, or they can pick anything, or how is so how do they put down these positive correlations, or even the terminology they use? Are they given somewhere, or
So yes, very good question. In the pre-lab, we talk about the different relationships that can occur.
in
And
the
so
lab, it's in the lab instructions.
that's true. I didn't print those out. It's all,
So
yes. If you open up the lab instructions, it's there. Great question.
everything is guided. The students, we assume they know nothing.
Mm.
And so they're guided on all of this. And because we're jumping around, it's hard for you all to see where it's coming from.
Okay, got it. Yeah.
I have one question. This is for the first physics class. Is this a calculus-based physics class or the algebra trig-based?
It can
Are
be
you
used for both.
For both. I'm sorry, did you say you use it for both?
We use it for both,
Yeah.
yes.
Okay.
But it, you know,
'Cause they're
I
all
only teach
taught in the
algebra
same
based, so I
place.
only use it there. But Kathy's setting has both.
Uh-huh. Well, I like the way you had them state the outcome, but put the restrictions on it based on the angle, the mass, and the length of the cord. For them, again, to get the idea, if we alter, we can see some different things.
All right, you okay with going to the next lab? This is all part of that 3-week series. So the second lab introduces them to error analysis. So they determine ranges of uncertainty in their measurements, whether we're using scale error or measuring techniques such as the stopwatch, or quantifying it that way. We have them identify and reduce experimental errors. So we start them out with the stopwatch, and then after they measure the uncertainty this week, then they realize, geez, there's a lot of uncertainty when you use a stopwatch, and we talk about that and why. And then in week 3, we're going to give them another measuring device that reduces uncertainty, a photo gate, which you guys are familiar with, but students aren't. So they consider the measurement uncertainties when interpreting the data outcomes as well. And so we talk about the error bars in Excel and what they mean and how we can use those. So at this point, the students work through all those uncertainty tasks using their data from Lab 1. So from Lab 1, this is actually the same data, but now they have some uncertainty bars there. And so with the uncertainty bars, there's a lot of overlap for mass, and we talk about what that means. And for angle, particularly small angles. So then this data looks really good because that's actually, those error bars are with the, is that with the photo gate, Kathy? I would
No,
think
it's still the stopwatch, but remember,
you were doing it.
you're going a bigger range. Like your
Ah.
time is so much different.
Good point.
Your scales aren't the same.
Ah, yes. That is something that is good to show the students as well. So
How do they get their error bars? What do they base that on?
So go ahead.
the error bars, that's sometimes you use scale error, but sometimes you'll use the measuring technique error. So if you have a data set, we can calculate the standard deviation in Excel and use that. But that's up to the instructor to decide ultimately. But we do, in the instructions in Lab 2, we talk about standard deviation and how to use that for quantifying.
Right, so they're guided through all of this. They're not expected to come in and know how to do this in Lab 2.
And that's why we spend that whole 2-hour lab working on the uncertainty, because they don't know this stuff going in.
And they're going to use it the rest of the semester.
So here is length, and this is real student data from Lab 2, where they had 3 data points. It might have been one of your groups, I'm not sure. So they had the 3 data points. Hopefully, we catch that during the instructor checkpoint, but in reality, sometimes lab doesn't always go perfectly and some slip through. But here, it's not as critical for length because we are going to have them do that again in Lab 3 with a better measuring device. So, but we do have the opportunity to talk about what the error bars mean and why 3 data points is not going to give me very compelling evidence to support my claim. So here's another set of data that students took. And then finally, another set. So this one, they used inches. So obviously we don't actually encourage the English units. We try to get them to use the units that, the SI units. And you notice this table has the dependent as time. Well, that's not really what we measured. We measured period. And there's a difference between the two, and we get to talk about why period and time aren't actually the same thing. They have the same units, but they're not the same thing. So finally, we get to lab 3. And lab 3 is where we have them create experimental models. And this is where they begin to actually construct knowledge through the creation of these experimental models in Excel from their collected data. And they have to identify the limitations of their experiment, describe the impact on the interpretation of the data for making the claims. So it's about their data and interpreting their data. And that's the key. It's not trying to find the right answer. It's trying to collect data and use it to make the claims. So they synthesize their information and make a data-driven claim that they then include in their lab report. So students repeat the experiment from lab 1 only for length, because we do improve the measuring technique there using the photo gate, because they've determined that from lab 1 that mass and angle, at least for small angles within a certain limit, according to what their data told them, as long as we control for those, then they do not have an effect on periods. So then we can just focus on length, and we can spend time creating those experimental models. So lab 3 is, this is what it looks like. So developing an experimental model. So these are the instructions that you can pull up in, let's see, we're actually, you can pull these up in OneDrive if you'd like, but I've got the instructions, at least the beginning of the instructions on these slides. So determine the IVs not to include in the mathematical model and provide evidence for the decision. So this lab 3 is when they decide, okay, does mass affect? And if not, can I reasonably not include that in my mathematical model? I still need the data, and I still need that claim and the relationship, because we tested it and we have to determine that it doesn't belong in my mathematical model. And we do that for mass and then angle within a certain limit. And so for each IV, the group will determine that doesn't impact the period of the pendulum. You have to include that and the evidence that supports that decision in your lab records. So mass and angle, and at least for the data that I showed you, angle less than 20 degrees should not be. Those do not have an effect on period. And then we repeat the experiment by using a photo gate, which reduces the uncertainty, and we get better data collection there. And they have to, you'll notice that in these slides, sometimes it'll say check by your TA, but you can just insert instructor there for, at least to your colleges that I know of, usually just have the instructors, and you are them. So then we design the experiment very similarly, just for length. So at this point, the groups, we have 4 groups, so we'll just use these first 4 and have you use that data set to create a mathematical model. So basically take the data set, put it in Excel, and create your mathematical model. So I'm wondering if I can make this a little bit larger.
This file, Krista, is in the folder for lab 3, so they can just copy and paste it. They don't have to retype it.
Ah, okay. Let's see. So lab 3, thanks. You can go into lab 3, creating mathematical models, and get that file.
Go to the next, yeah, there you go.
And so we've got the instructions, the the directions tractor will open the instructions. The data manager will create the Excel file, and the data recorder will make sure that students, or they would create the lab records. In this case, let's just create a graph from the data set.
So that Excel file shown there is the actual data file you just showed. So whoever's the data manager, they can open that Excel file and the data's right there.
All right, so group 1 is Trina, Erica, Haiti, and Nicholas. Group 2 is Aditya, Cyrus, Lara, and Negagusi. Group 3 is Andrew, Chelsea, Randy, and Vijay. And group 4 is Connolly, Kashab, Kareem, Dakum, and that's it. So what questions do you have before I open up the breakout rooms?
So I guess the question is, do they know what to do? So when you get to the breakout room, you're going to start with the instructions on I think it's 1B. Is where it starts with the photo gate. And just pretend you're a student. Oh, there it is, 1C.
So section 1, part C is where everyone should start. And where are we going until?
Until they get the graph done with the curve fit, and you have your mathematical equation. I
So
can give you the lab instructions, and we can send a announcement where to stop.
what questions do you have?
How do we know the roles that we are assigned? Does it show up somewhere?
You guys decide.
Oh, I see. Okay.
Okay, I do have a question on, when I'm looking at the contents of the file. Mine only goes down to where it says room 3, lab 1, but I can't go beyond that. How do I get to the next page?
Well, I didn't open up the breakout rooms yet. Is that what you're asking?
No, for the instructions for this, where it says lab 3 creating experimental models.
I think it's in the PowerPoint.
It's in the PowerPoint.
No, you should not be in the PowerPoint.
I'm not in the PowerPoint. This is. Oh, crap.
Maybe, Krista, you should open your OneDrive folder and show them.
Oh, I wasn't sharing. I meant to be. So, yeah, let me share that. I just did open that, but it doesn't do any good if I don't share it.
No.
All right, so are you in the folder? We're going to go to lab 3, creating experimental models updated for spring 2024. You with me?
Hold on. Okay, I found it. I found it. Oh,
Okay.
this is so good. The accident
then-
that I was in was supposed to be on my foot. I think it kind of affected my brain a bit.
And then PhotoGate data for instructor use. We open up that and it has the 3 groups, or actually it has all the groups. So download this to your own device or your own cloud storage so that we're not messing up the main folder, and pick length. Whoops.
That's the answer, Krista.
That's the answer. Sorry about that. Didn't mean to do that. Lab data to give to students.
Right.
So don't cheat and look at the answer, apparently.
Whatever your breakout room number is the number of the group you should be for the data.
Yeah. So if you don't know which group you're in, I'll bounce around and let you know. All right, I'm going to open up the rooms. If you still have questions, stick around and ask. Otherwise, you can go to your rooms and graph your data.
Hello. Ooh.
All right, you could probably pause the recording if you wanted. Look. Great, I think everyone's back. Okay, so we'll go back to sharing the screen. Thank you guys, you did a great job. Some of you did even more than what we asked. And sometimes our students do that, but mostly that's probably more due to the fact that you guys are really instructors. So, but thanks for what you've done. So what we have them do is we have them share their data in a OneDrive file or on the board or however you want to do it in your particular classroom. And so each group would then put their experimental model and their control values. And since we're using data we gave you, I went ahead and put in the experimental models and the control variables that I would expect students to have for each set of data. So how does your experimental model compare to what we have listed there?
It's perfect. I'm group 2 and it was exactly 2.004.
So one of the things I noticed in one of the groups is that you went beyond just the power fit and you tried to linearize the data, which is a valid scientific method. But here our purpose is to be able to tie this back into the scientifically established model. So we don't want to do that for this data. And so we stop at this model so that we can have the students draw conclusions from the above. So from this, we have 6 different sets of data that students took that you guys created these models. What conclusion can be drawn?
Well, the power on the mass of each one, I think so they are, no, is that second per the power value, the exponent on each one of the values is very close to 0.5.
Excellent. So you notice that the exponent means something, and the 6 different groups all had approximately a 0.5 or a rational exponent of 1/2. And so that relates to a model that says that our period is proportional to approximately 2. Look at our coefficient, they're all approximately 2 times the square root of L. And proportional, why do I say proportional instead of equal?
I think that's approximately, I mean.
Oh, approximately. Okay.
Because of our measurement system, I think would be.
Right.
We
So
have to have a better way of measuring the length.
So, but the other thing, not only there's a relationship, but then there are conditions for that relationship. And those conditions we take from the control variables, that when mass is and angle are constant, an angle is less than 20 degrees. So we have different masses for these different models, but mass was held constant in all cases.
I'm just curious, I'm sorry.
Yeah, go ahead.
In the first column, that m to the power, what is that meant to represent?
That's the units.
M point, and how do you get a power 0.4995? I'm not sure what.
Because that's the unit on L. That's the
Oh, I see. You're doing that. Okay, I got it. I was looking
so
at
the students they're led through dimensional analysis here.
Okay.
And it takes some pulling along.
Okay, yeah, I can see it, yeah.
And it should bring back, if they've had good algebra, that the power on M like that, it's a root expression.
Mhm.
In this case, 0.5 would be a square root.
Yeah, okay.
M to the
Okay.
1/2 power.
Yes, it is a 1/2 power
Yes, yeah.
or exponent.
Okay.
So this is bringing us back to the theory evidence coordination framework. And so if you notice now, we're in the bottom right corner where we want to take our model and compare it to the established model. So part of my screen is covered by the bottom bar. There it is. Go one more click, Chris. There you go. So when the students see the scientific established model, they question, well, what does the 2 in our model mean? And it must be 2 pi over the square root of g. So they'll do the calculation and they find out that's 2.01. So this model or this experiment lends itself very well to getting really good data and matching the model very closely. So it's a great experiment to start out the semester with. So here's the organizer that Krista mentioned earlier. And now we're adding the established model to it. And if you'll notice, everything matches really well until you get to the bottom, because we couldn't test for G. And the whole reason we want that model is what was at the bottom of the screen. We're trying to teach the students causal reasoning. That's really what we're working on in our new updates to the curriculum now. And the only reason you can have a causal relationship here, I can say the period is caused by a change in L if G is constant. So that's what that bottom brown font at the bottom of your screen is referring to. Did you want to add to that, Krista?
Well, just one thing that the earlier outcome organizer had listed the control variables there, and it gets kind of busy. So it's in the instructions for this lab, they're put off to the side, I believe now.
It does say constant G on there.
So what do you think about this idea? Once you get to this point where, okay, so you've established the connection with the length, with the mass, the angle, and of course, gravity is a bit of a problem. How about inserting a simulation at this stage, just for that point where you can actually modify the G value and see what it could do?
That's a great idea. I never thought to do that.
Yeah, because the FET simulation on the pendulum is great in that it has multiple G values. And I prefer the idea of experimentally connecting the period to the length and the angle, and then as a complement with the simulation for the G value.
I mean, I guess my only thought though is students will say the FET simulation is based on an equation.
Yeah,
We programmed it.
yeah.
But they could at least see it. Yeah.
But one of the things about this lab curriculum is that you as the instructor can choose the parts that you want to use or expand where you want. It's up to you. And so if, like if you have the time in your semester to do that, and that's a valuable skill for the students to have, then by all means, go for it. I think that's a great idea.
Right. You have access to all the files, and we left them in Word on purpose so you can change them for your use.
All right. So the question prompts, did you want me to go through that, Kathy?
Yeah, you can just do it quickly if you want.
Sure. Okay, so at the end of all the labs, there's question prompts, and the purpose of these wrap-up questions is to get the students to realize what they need to include in their reports and their lab records. So these prompts help students make better judgments about their data and their claims, and then support it with evidence. So should measurements collected be when testing each independent variable be trusted? Would you expect similar numbers and or similar pattern of it if the experiments were repeated? So we talk about the range of uncertainty, the pattern of the plotted data, and should you trust this to make accurate predictions? And so we talk about the trend line, the R-square value, how that supports what your claim is, the range and number of independent variables, the controls. And the last two here are similarities to the findings of other lab groups, which is why we share the model and the conditions that the other lab groups used. And then also they have to address the similarity to the scientifically established outcomes. And then the question prompts are also guide the students to see if things make sense. So how they can make sense of how their outcomes fit with their own ideas and the established model. So that TEC framework, they're relating it back to their own ideas as well as connecting it to the scientifically established model. So another 4 questions: how do your findings relate to what others have done? Does the experimental model make physical sense? And then, as with all experiments, what are the limitations of your findings? And so that the students recognize that there were limitations, and there always are, and we have to include those. What are some suggestions for further investigation? So we're modeling the scientific process that we have for any scientific experiment and claim.
Krista, there's another lab that I do at the beginning of my class, which I'm not going to go through the details, but in the process of doing it, they have a very crude measurement system using cinder blocks and estimating to 1/2, 1/4, and 3/4 of the cinder blocks in the response. But then we gather the data, we do the graphing, we get some kind of example for it, and eventually they realize instead of having to do this all every time to get a relationship that we're looking for, instead of having to go back and do the lab over again, we learn to write a rule for the data, which leads us to the equation. But at the same time, I give them a chance to test the extremes that it goes beyond. And they find out that the equation that worked for their small distances does not work for a larger distance. So then that leads them to the equipment we were using, and was there something that we left out of the initial part that we didn't explain? And
So that's a good thing to consider.
So
we need to actually go on to the rest of this curriculum.
Yeah.
Okay, thank you for sharing. So we've got lab reports that I wanted to touch because we are kind of running short on time and probably your energy. So we've got lab reports that the students complete, 4 of them during the semester, and they have 1 design challenge at the end. And so we have the listed research questions for the rest of the groups of labs. And every lab is actually 2 weeks long. So they have a lab record for each lab, but then a lab report for the set of labs. And so the lab report is going to be part 1 will be the experimental design, data, and analysis that they did in class, and they've already submitted it. And then the part 2 is the conclusion that they individually write. So lab records and the data analysis, they're done in a group. The lab reports, each student has to develop that ability to take the conclusions from their data and put it into words. And so that's what we're trying to get students to have, that skill, but also learn how to work in a scientific community. And there's a rubric in our learning management system. What?
I just say the lab report is not like this full-blown 20-page report with a procedure and all that. We want to know, can they write an argument based on their data? And so they're given very narrow guidelines to make sure they're writing a clear argument. That was it.
Sorry. So this is just the list of our different labs that we have. And so because of all the breaks in our, the days off, we end up with 12 labs during the semester, plus the final. So the research. We have some research that addresses what impact does the lab curriculum have on the student ability to generate a written argument, which is the lab report that Kathy was referring to. And the focus is on generating that argument and supporting it. And then also, what impact does the lab curriculum have on students' development of selected scientific reasoning skills? Because we advertise this as lab curriculum that actually builds scientific reasoning skills. So we do have some data on their lab report grades, but we've really upped the ante. We really expect a lot more now than we did back in 2012. And so that will be.
Well, 2012 was before we revised the curriculum.
And as the years go on, we keep asking more of the students because we found better ways to elicit good arguments from them. But the scientific reasoning skills, there are a lot of different scientific reasoning skill dimensions, and they're listed here. And if you've read the work of Lawson, you probably have seen some of these as well. But we focus on 3 of them, which is control of variables, data analytics, and causal decision making. And those we actually have a validated instrument, and the article that Kathy was referring to is validating this instrument. And we have about 12 questions that measure different levels of control of variable skill. So we have data analytics, and those are the different areas that we measure, and causal decision making. So this assessment can be used as a pre-post assessment. And if you are interested in using the assessment, then Kathy can connect you with that. And here's an example of a control of variable question. So we have glass tubes, we have red light that is shown on those glass tubes, and they're on a surface that's transparent. And this experiment shows that flies respond to, and students have to answer what do they respond to. So we have a variety of questions here, and that's a control of variables question. This is a different style control of variables question where it's asking what can be tested. And these are in the PowerPoint, so you can go through those individually. Plus, if you're interested, we'll give you access to the actual assessment tool. Data analytics questions, there's a couple here. One about using a 6-sided dice, and another one about product quality. So asking, based on this result, what are the following statements can be concluded? So getting them to do some data analytics. And then this one is a little bit longer, but it's basically asking about, from a recent news article, that it suggested that students' math scores on SAT can be linked to how long the student has participated in music lessons. And it asks for a possible explanation. So this is a causal decision-making question. And so those are the selections based on the data, and then we indicated the answer as well. Did you want to talk about this, Kathy, or should I keep going?
I can just talk about it briefly, as long as you can still hear me, okay? Okay. So those are the 3 question domains that we're really interested in. And control variables, the red line, is something students respond to pretty easily. But the orange line at the bottom, causal decision making, is really challenging for students. So our graphic organizers and our question prompts and our pre-lab activities are very much focusing on that reasoning domain now. And I think that's a 6% increase. And prior to using this curriculum, that was a horizontal line. So that may look like a tiny shift, but that is like gold to us right now. So that's all I need to say.
My data at a tier college before the graphic organizer was a negative shift for causal decision making. So I'm really hoping that this data that I have from this past fall, that I have something better to say than what I had previously. So I'm hoping it helps. All right, so what have we learned? Well, most 21st century skills, the skills that we need students to have, aren't actually effectively developed in traditionally content-based teaching. So often that content-based teaching triggers memorization type of learning, and we're focusing on process-oriented instruction, which is the inquiry style of instruction, so that we can foster students' higher level abilities, including scientific reasoning. So we need to change the emphasis from outcomes or content to process or method. So we're focusing on developing their skills in lab by repeatedly giving them opportunities to practice, and their skills do actually improve. So key takeaways for modifying your labs. We need to identify clear measurable skills-based learning outcomes map out a course with scaffolded learning outcomes. So each lab or group of labs, you need to know what you want the students to get out of it. And our labs include what we think students should get out of each lab week. Provide students with repeated deliberate practice, and we make use of both hypothetical and real scenarios. We choose contexts that practice the skill at appropriate level and time. So we start with a pendulum, but then we move on to other contexts and ask a little bit more throughout the semester. We've got embedded TEC, which is theory, evidence, coordination question prompts that guide, and the graphic organizers that guide the students' thinking. And we consider the use of all the course components. We think about what are the students going to do before lab? What are they going to do during lab? And what do we want them to do after lab? So we utilize all of that. And then design the assessments to match the actual identified learning outcomes. So our last activity, we'd like you to think about where in the curriculum could you target learning objectives that focus on theory, evidence, coordination? And how do the wrap-up questions support your learning objectives? And then discuss in your groups how you could change one lab activity to target these associated skills that we're focusing on the lab curriculum.
So Krista, could I jump in real quick?
Yes.
In case people have to drop off, I could either share my screen or you could pull up the OneDrive folder. I just want to point some things out there.
Do you want, you can share so you can be in control.
Is it showing?
Yes.
So in this folder, there's this first file says start here. We threw a lot of information at you today, and I don't know how you'll ever remember any of it, but these files talk about a lot of the stuff we mentioned today. It talks about the framework, how our content is organized each week, and I'm not going to read that to you. But here's the framework, and it talks about the learning outcomes for each lab. So you can see that there's a logical pattern to how we put this together. And the last thing I want to show you is that every folder contains everything that you need. So you didn't get a chance to look at these files, but there is an instructor version. So the lab that you did today has a lot of notes to you as the instructor, even to the point where when there's a checkpoint, it talks about what you should talk about with your students. I don't know why it's not showing up in blue. Oh, here it is. And the reason we had to have such clear notes is on main campus, all the labs are taught by graduate students. So we have to give them a lot of tools to be able to teach. And the last thing I want to point out is that all the pre-labs, all the quizzes, everything is in the folder. You just have to spend a little time poking around and looking at it. So I just want to share that with you. How do I stop sharing my screen?
Kathleen, the quizzes that you have on the content reasoning that we were looking at, are those questions that your group wrote up for this?
Everything that's in that folder we wrote, yes.
Oh, okay. Well, I'm intrigued by those questions. You did a very good job.
So
she's worked a lot of years on it too.
yeah, well, we've got funded twice now, so NSF helps.
Yeah.
But we threw a lot at you, and everything is written in the lab instructions for the students. So we tried to make the job easy on you as instructors, but really easy for the grad students that do the teaching. So I'll turn it back over to you, Krista.
If you have interest, I just opened up one of the IFETs. Oh, there's a question. Let's go with the question first. Nagusi?
Yes, I have a few questions. The first one is, I know you are using Excel, but did you make a choice of Excel compared to like Logger Pro, for example, does similar things? The graphing one, which we have, we subscribe to. So was that a choice that you made?
Yeah, so the students in our engineering program already know how to use Excel, and they need to know how to use it in their other courses. So we made that choice for that reason.
Okay.
So at my two-year college, we made the choice because we use Vernier's LabQuest 2, and our laptops were removed from the lab during the pandemic because we weren't in the lab, and they never really came back. And then when they did come back, they didn't have Logger Pro on them anymore, and it became a fight of technology. And I knew I had students had laptops and they have Excel, and so I knew that would work. And they have the LabQuest 2s, which graph for them, but it's not as easy to get that into a computer unless you have Logger Pro. So Excel works whether you're, I think on main campus, they use Pasco data collection. So that works fine there. And if you that is your choice. If you want to use Logger Pro, that's fine too.
Okay. My other question is, so for example, this pendulum lab extends over 3 weeks, right? So it's very nice. The students will really get a lot out of it, and from what I see, and that's really well done. So if you do this, so in the 15 weeks that you have, I saw a number of labs. How many of labs, similar labs? I'm assuming 4, 5 at most, but you listed about 10, 12. So are they like candidate for this kind of work, or how many do you do in this manner?
So I just pulled that back up and I'm going to share it here. So the first 3 use a pendulum, but they teach different things each week. On main campus, they use projectile motion to apply those skills. And then force and motion, so basically Newton's second law, testing the factors in week 1 and then extending that in week 2. Simple harmonic motion, developing the mass on a spring formula. Rotation, what affects the moment of inertia of a rotating system, and then the wind turbine design. So there's 12 weeks of labs, but they're mostly grouped in 2s.
Okay. So there are, okay, I see it. Yeah.
So the first time that you implement this, sometimes things don't go as you plan and it takes longer. And if you're really time limited, I've had during the pandemic in particular, sometimes we needed both weeks because I just couldn't get students to move along. Before the pandemic, they did really well, but it's been a challenge with the students that I see now sometimes.
Okay, thank you. And one last question. Are the assessments for these labs, are they produced, created by your group, or they are available somewhere?
The pre-lab quizzes are in the folder, and that's just a formative assessment, but that they do before class. The lab records and the lab reports were created by Kathy, and that's in those assessments. And do you have the rubrics in there too, Kathy, or just?
They're supposed to be.
I thought they were.
Occasionally one's missing, and I've been filling it in.
So the rubrics are, what we put into our learning management system to grade those. And then the final exam is something that we've created, yes.
Okay. The pre and post ones are the ones you created too, right?
That, yes, and our other research member, Leibao.
Okay.
Yeah.
Thank
We
you.
call that the I-STAR, the Inquiry for Scientific Thinking, Analytics, and Reasoning.
Okay, thank you.
And if you want a copy of that, reach out to Kathy or me, and we'll get it to you.
All right, thank you. I will. Mhm.
Erica.
Yes, I want to ask Krista, in this case, for example, for you doing this job, a good job in this laboratory, doing this different part inside the class, how much a student do you think is the best quantity for doing this job?
So I actually have a really ideal situation. Kathy has 24 students in her lab, and I have 12 because they renovated our building and made our lab spaces small. And so it makes it a lot easier to actually handle 12 students. Sometimes I get up to 15, but so I'm a little spoiled, but don't, too bad this is being recorded. So it helps to have the smaller classes.
Okay, okay.
But Kathy does a really phenomenal job with 24. I think that would be a bit harder.
Well, it's our grad students that have to teach. We faculty are teach the lecture only. But we train them, and we train them how to sometimes several groups have to do a checkpoint at the same time because we have
Right.
some groups.
Okay, thank you.
And I use whiteboard meetings also to kind of do a whole class check at times, just to keep things rolling. So you get to kind of decide how you want to handle it as well.
Good. Thank you so much. There are a question in the chat.
Let's see. There's a couple people asking for access to the folder in the chat, Kathy.
Yeah,
So
I'll get it to them.
yeah, so she'll make sure you get that. Do you guys have interest in going in breakout rooms and talking with a small group on how you could implement some of this? If you do, I can open the breakout rooms. Otherwise, we can continue the conversation here.
Okay.
I'll open up the breakout rooms and you guys can decide if you want to continue asking questions, I'll be here. And so will Kathy.